So sodium check. So you just need to log in with another account that is not your account so that I can copy. You are getting that copy. That's my phone. And if you have more than shared, you want to it's fine. Immediately.
You can share that.
Of course. Uncle, I'm following my boss.
Why not?
Sodium. No, me, I'm already using it. Auntie. The link. I've sent it to the group. But you have share so that group.
Let's try keep quiet. So we've done, how many topics have we done? How many have we done today? Three. So we did electrostatics, we did Coulomb's law and electric field, and we've done capacitors. So let's move on to current electricity. So at the beginning of the class, I told you the difference between current electricity and electrostatics. Abi? So when you talk about flow of charges, they are talking about current electricity. Now, this bulb is able to come on only because charges are flowing. If the charges are not flowing, the bulb will not come on. And that's why you can switch it off if you don't want charges to flow. And you can switch it on if you want charges to flow. So, current electricity is simply defined as the study of flow of charges. So, the study of flow of charges. And when charges flow, what do you get? Electricity. So, the moment charges flow, you get electricity. Now, when you're talking about current electricity, it comes in different ways. We have symbols we use when we're talking about current electricity. If I have something like this, Now, you remember I drew this the last time. This is a battery or a cell. This part is negative and this part is positive. Now, when electrons start flowing here, the next thing you will see is that when I close this thing, the bulb will come on. If I leave this thing open, the bulb will go off. Now that means when I close it, charges flow. When I leave it open, charges do not flow. So the flow of charges is what we call current electricity. Now, from what I have here, I'm able to identify this as a bulb, this as a resistor, and this as a battery because I know the symbols. So the paths through which your current flow, we simply call it circuit. So, without wasting time, it is still an introduction. So, we said charges must flow. What paths will that charges flow through? Through a circuit. So, the charges continue to flow in this place, and that is called a circuit. Now, we have different types of circuits. But before I talk about the types of circuits, let's look at the symbols you might get to see oftentimes. So if you see a symbol like this, in current electricity, this is called an ammeter. That's an ammeter. And the function of ammeter is to help you detect the current that is flowing. So that is it. We will talk about it again. This is called a voltmeter. You remember when I did capacitor the other time, I told you that I can measure the work done across this place. The voltmeter is used to measure the work done across a component. So this is called a voltmeter. We will talk about it again. Then you can have something like this. This is called a galvanometer. The galvanometer is used to also detect electric current. So this one is used to measure electric current. That means what is the amount of electric current that is flowing in a circuit? The ammeter will tell you. If you want to know if current is flowing and you just want to test if current is moving, then you use what we call a galvanometer. Then if you want to know the amount of work that is done across a component, probably across the resistor, across the board, then you will use what we call a voltmeter. Then another thing you might get to see is this, which I've been showing you often. This represents the positive parts and this represents the negative parts. Now what we have here is called a cell. Collection of cells. So if you have several of them together, then we call that a battery. All these symbols, you'll be seeing them as we're moving on. It's just the introduction. So collection of cells is called battery. You can also have something like this. When you have a symbol like this, or the symbol can also look like this. This symbol is called a resistor. You will know what a resistor is as I'm moving on. Now, you can also have a symbol like this. This symbol is called a rheostat. A rheostat. What's the difference between a resistor and a rheostat? The rheostat you can regulate. The resistor is constant. You already have a value for that resistor. But you can be changing the resistivity of this one. We'll talk about it later. Then we have something that looks like this too. If you are seeing all of these components in a circuit, you should know what they are saying. That's what that part is talking about. So if you have something like this is called a jockey. All of these are important in current electricity. If you have a symbol like this is called a switch. But this switch is open. Another way to have an open switch is when you have it like this. But if you have it like this is called a closed switch, which can also be represented like this. So this is a closed switch, this is a closed switch, these are open switches. Now, those are symbols. Another important symbol you might get to see is this. This symbol is called a diode. And you talk about it when you get to study semiconductors. So, if you want to have a circuit, that's what you can have in a circuit. But the most important ones are, let's look at this circuit. The one I just drew now, let's say this is a bulb connected to this, then connected to this, and this is connected to this. So you're going to tell me what each of them represents. Connected to this, connected to this. So looking at that circuit now, that's a complete circuit. And this I told you what's a circuit? The paths through which charges flow. Abi, that is a circuit. But I'm still going to talk about it again. Now, in this circuit, charges want to flow. What does this represent? Which part is negative here? The smaller one. It's something you need to know. This part is positive. What does this represent? You can call it a key or a switch. Is that taken? Now, this key, is it open or closed? Open. Look at this. What do we call it? What is the function? When charges are flowing, current will flow. So, if you want to know, I'm going to tell you how current and electron flow. If I want to know the amount of current that is flowing here, I need this instrument. And that's what ammeter will do. So it will tell you the amount of current. Now, that current will pass through this guy. What do we call this guy? A resistor. Abi? So this current flowing through the resistor, what will be done across that resistor? What will measure the work done? What do we call this guy? Somewhere here. That's a voltmeter. Abi? So it measures the amount of work that we do across this guy. That's what we did in the first class. I can also put a voltmeter here to measure the amount of work done here. So this is a load. We call this a load or a bulb. So that is what we are just talking about. So now, when you're talking about circuits, we have not started. This is just introduction. So I said, before this bulb can come on, current must flow in the circuit. Abi? So the path through which current goes is what we call a circuit. So it is the path of flow of charges. That is a circuit. So the path through which charges flow is a circuit. We have three types of circuits majorly that you need to be aware of. We have what we call an open circuit. When you hear the word open circuit, current does not flow. So in an open circuit, you are not allowing current to flow. In this case now, in this scenario, can this bulb come on? The bulb cannot come on because the key is left open. Is that taken? That's what we call an open circuit. Is that taken? Then we have what we call a closed circuit. In a closed circuit, that means that the key is what? The key is what? Closed. We carry on. So the key is closed, and that means that current will flow. So current flow. And why is it that current flow? Because key is closed. So we call that a closed circuit. But here, key is open. Key is open. Here, key is closed. Now we have what we call a short circuit. A short circuit, key is also closed. But the problem there is that when the key is closed, is current flowing? Is current flowing when the key is closed? Now, if current is flowing, the current will not be allowed to pass through load. They carry on. When the current is not allowed to pass through the load, then we said that it is a short circuit. So what's happened in that case is that you can just connect this thing to an external source, you divert the flow of the current. So that current does not go through the bulb. As the current is going, it only passes through another channel and it continues. So the bulb will not come on. And that short circuit, you can have it in the house. Sometimes you can switch on your bulb, other things will come on, but that bulb will not come on. Current is flowing, but the current is not getting to the bulb. So that is called a short. So it's probably an error in the circuit. So those are the three parts we have. So if I switch off these lights now, I've left it in what? Open circuit. If I switch it on, then it's called the what? The closed circuit. But when I switch it on, and it's not like this thing is faulty, but the current is not getting there so that it comes on, then that is called what? A short circuit. Do we get the difference? So now, how does charges flow? If you have a circuit, let's draw a simple circuit. This is another question they can ask you. You have a circuit. You already know what all of these guys represent, which I will talk about again. Now, this negative part, you need to know something. Electron or charges, they move from negative to positive. So in a circuit, electron move this way from negative to positive, while currents moves from positive to negative. I hope you're following. So current moves in opposite direction. So we usually call that conventional current. So it's something you need to know anytime you are asked. If the electron is going this way, current moves in opposite direction. So that's one of the things you need to know. So now, what is an electric current? So let's define an electric current. So now that you understand how the circuits operate, let's define electric current. That's the first term to start with. So, electric current. So, what is electric current? Electric current is defined, I said current is moving in this circuit, Abby. So, electric current I is defined as the rates of flow of electric charges. The rate at which charges move, the rate at which electrons are moving, the rate at which charges move in a circuit, then we call it electric current. The more the electron, the more the charges, the more the currents. Shake that. It is like the result of electron is what current brings out. So the result of electron flow is what you see here. So generally, you can just say Q is equal to IT. I think that's the general formula you used to have. So your electric current is defined as the rate at which charges flow, and that's time related. So now another thing you need to know is that what determines the amount of current, it depends on the number of charges. So you can have one electron carries a charge from basic chemistry, carries a charge of 1.6 times 10 raised to the minus 19 coulomb. So just one electron that is moving, it's moving with this amount of charge. How about if I have 23 electrons? You know there will be more charges. Abby? So now, how do you know the number of charges carried by several electrons? So the formula is Q is equal to NQ. This N is talking about the number of electrons, not even number of moles now, number of electrons that are flowing. But you know that in one mole, how many electrons do I have in one mole? And hey, Jesus. Basic chemistry. One mole of electron is what? That's 6.02 times 10 raised to 23 electrons. So if I say I have one mole of electron, it means this is the total number of electrons. So if I now say calculate the charge carried by those electrons, That means that will be Q. What's my number of electrons now? I'm not saying one. I didn't say one electron. One mole of electron. This N represents just one electron. Do you get that? This Q is the total amount of charge. We have talked about that. But for one electron, Q will be equal to this. But for one mole of electron, that means we are going to have 6.02 times 10 raised to the power 23 multiplied by the charge, Abi, 1.6 times 10 raised to the power minus 19 coulomb. This is an approximated value that you have as 96500 coulomb that you always called 1 Faraday. So 1 mole of electron carries this total number of charges. So 1 mole of electron is this. That means if I say 1 dozen of electron, how many electrons do I have? That's 12 electrons. So if I say 1 mole of electron, that means this is the total number of electrons I have. And if 1 electron carries this, then 1 mole of electron will carry what? Then that will be this multiplied by that. And that will give you approximately this. I hope you're getting that. I'm just explaining that, but note this formula. Your N represents what? Number of what? I said this N represents what? Is it number of moles? It represents number of electrons. Do you get that? Number of moles is different. 1 mole of electron, you can now multiply it. Because 1 mole of electron is not 1 electron. I hope you know that. 1 mole of electron means this is the total number of electrons. If I say what is the charge carried by 1 dozen of electrons, what will you multiply this thing with? 12. Do you get that? That's what this formula represents. So this is the number of electrons multiplied by the charges. So if I have 10 electrons, then the charge will be more. If I have 20 electrons, the charge will even be higher. So depending on the number of electrons, we are just introducing basic chemistry here. Like if they now say 1 mole of electron, that means they are telling you that this N is what? 6.02 times 10 raised to the power 23. So don't go and put 1 here. That will be wrong. This one is majorly for if you are writing wave, you can see this in wave. So now, but this is for everybody. Now, if electrons are moving, one thing you need to note is that how to measure this current. So how do you measure current that is flowing? I've talked about that. What instruments do we use to measure the amount of current that is flowing in the circuit? Ammeter. But you need to note something. In order to know the current that is flowing in the circuit, we use an ammeter. This ammeter must be one connected in series. Let's go back to what I taught you this morning. Let's say this is a circuit. It has this. So I connect my ammeter. There's a way you connect it, positive, negative, and no, but just for classing. Then I also have these circuits. Then I connect my ammeter here. Now, looking at what you have between A and B, in which one is the ammeter connected in series? A. Now, what do you think will be the problem with the second scenario? You know my instrument is ammeter. If I connect it in series and I connect it in parallel, I want to measure currents. So now, the number of electrons start flowing. They should have been around here. The number of electrons start flowing. What do you think is the error with the parallel from what I taught you in this morning? I want to know the total number here, and I also want to know the total current, not electron. But funniest thing is when the 4 gets here, at this point 2 can go here, Abi, and 2 will also go here. Now, if 2 should go here and 2 goes here, what will this ammeter read? It will only read for those 2. But for this one, it will read for the what? For the 4. Do you get that? So if you connect it in parallel and you are trying to check the current that is flowing, then there will be an error, because that is not really telling the entire thing that is flowing. Do you get that? Only when you connect it to series, that's when it will tell you. I'm telling you this because they can ask you that is your ammeter connected. Your ammeter must always be connected in what? In series. Do you get that? You know, the purpose of connecting the ammeter is to measure the what? The amount of current that is flowing. Now, if 4 electrons are flowing and they are giving current, but now you are measuring for here, for same thing, you are measuring to here. So there's an error. So you don't connect in parallel, you connect ammeter in series. Is that taken? Another thing you need to know is that your ammeter, there's what we call resistance. Resistance is part of the components of ammeter. When you say the word resistance, resistance is defined as the opposition to the flow of current. It does not want current to flow. So now when they are building ammeter, ammeter has its own components of resistance. So if we're still going to talk about resistance rod, in an ammeter, the resistance I have inside, should it be of high resistance or of low resistance? So you see that it's not everything you have to cram. If you say that the resistance should be high and you want to use it to measure current, will it be able to measure it for you? Because you are saying that no, those currents will not flow and you want to use it to measure. I want to know the number of persons passing through this place, but I'm still telling people not to pass. How will I know the number of people passing? Do you get that? So now, when you connect your ammeter in series, the ammeter is built with a low resistor. So the resistance of the ammeter must be low in order for it to measure the entire current. Is that okay? These are questions they can ask you about ammeter. First thing is, what is ammeter used for? It is used to measure electric current. Abi, the resistance of ammeter, should it be high or low? It should be low. Why is it to be low? So that the current can flow easily. Since resistance is opposition to the flow of current. So now that we know what ammeter does, the next thing to look at is your voltmeter. There's an instrument called a voltmeter. Voltmeter helps you to measure the potential difference. It measures the potential difference. And if you're talking about potential difference, we've talked about it again this morning, but to repeat it, let me just take you back here. The potential is the work done in moving a unit charge, Abi, from infinity to a point. But potential difference is simply the work done in moving a charge from one point to another point or across a component in a circuit. Let me explain it better. Let's say you have a circuit like this. We are still going to solve questions at the end. So let's say you have a circuit like this. You have your ammeter. All of these things I'm drawing is so that you understand it better. Now, what's the function of a voltmeter? What is potential difference? It's from the formula. The work done in moving a key charge from one point to another. That's what we call potential difference. Now, I want to move a charge from here to here, like across the resistor. How do I determine the work done? The instrument without calculation that I need to plug is what we call a voltmeter. Now, why did I plug the voltmeter this way? You know, I want to know the work that you will do. Let's say this place is this work and this place is this work. So let's say this place is 20 joule, just for example, and this place is 50 joule. So to move from here to here, what do you think will be the work I will do? What's the amount of potential? if this place is 20 joules and this place is 50, that means across it, what am I doing? 30 joules of work. Do you get that? So at this point, I want to know the potential difference from here to here. I want to do work across this place. So in order to measure that potential, I must connect it across the 2 points. If it is this point I want from here to here that I want to know, what will I have connect it across that point? I hope you're getting. But if I had connected it this way, the way I did for this guy, do you think it will measure what I want it to measure? Because voltmeter will measure the work I do from one point to another point. So your voltmeter is connected in parallel. You need to know that. So for the first one, your ammeter is connected in what? And I just explained why you need to connect it in series. So they can ask you, how is your voltmeter connected in parallel? Now let me now explain something. I said something here that when you connect your ammeter, you have to have a low resistance. Abi? Now let's see for voltmeter. Should it be a low resistance or a high resistance? How? How did you know? Look at the connection here. When we talk about Ohm's law, all of you have seen this formula before. V is equal to IR. Abi? I'm going to talk about it next. It's just that current electricity, they used to enter each other. That's why. So now, looking at what we have here, V is equal to IR. I want to measure the work, this V now, but I want to do calculations. In order to do this, so listen to this, so please. In order to do the calculation of the work across this place, I need to know the current that is flowing across this place, and I need to know the resistance of this resistor. So if I know the resistance and I know the current, I can calculate the work done. Abi, from here now, how do I need to connect this voltmeter? If I'm connecting it in parallel, do you know that if current is coming, by the time the current gets here, what do you think will happen to that current? Let me use what you usually know, electron. Let me change this to smaller and this longer. Let's say 5 electrons are coming. Now, if these 5 electrons are coming, when they get to this junction, what do you think should happen to those electrons? You already know how you connect this guy, Abi, in parallel. So now, by the time these 5 electrons get here, when they get to this junction, like some parts we want to come here, Abi, and some parts we want to come here. And what gives me the current that will flow through this guy is the number of electrons that are passing. But now, the number of electrons passing through this now is not the same as what was coming. So I don't want electrons to pass through this guy at all. I hope you're listening. All of this will not make you to cram a lot of things. Carry up this now. All these parts are sensitive and you have to really listen. Now, all of these electrons here and here, they are the total of what you have here. But for me to measure the current that is here, I must let all of these electrons to pass through. So in order not to allow electrons to pass through here at all, I need to make sure that the resistance of this guy is very, very high. So that if the electron wants to pass through there, this one saying no, there is no way here. So they don't have a choice than to pass through this place. Did you get that point? Let me repeat. Your voltmeter, how is it connected? In parallel. But in order to determine the work done from Ohm's law, this is the formula I will use. So I need to know the work done across this resistor. Are you listening? So now, to get the work done across the resistor, I'll use this formula. V is equal to IR. So I already know my resistance for this resistor, which is R. Then I need to know the currents. To know the currents, it depends on the amount of charges that is flowing. If I release 5 charges, 5 electrons, for example, when they get here, because I've connected these guys in parallel with this, now, what am I going to have? I'm going to see that Fikayo. Can you go downstairs to school? So, please, I want you to pay attention. Now, if I have, there are 5 electrons here. By the time the 5 electrons get here, some parts can move through here, and some parts can move through here. Now, the parts moving through here does not justify the total current that is flowing. And the only way I can connect this thing is in parallel. So for it to work. So in order to prevent these guys from passing through here, I need to just put something that will make sure that this guy will not pass. So they can ask you, for a voltmeter, what type of resistor does it need? It needs a high resistance resistor. But for ammeter, it needs what? A low resistance. Are you following? Volume. So now, please, so it's not much. Current electricity is not much. So don't get tired. Do you want us to stop? Do you want to go? You people are already looking tired.
One is asking for you.
Yes.
Now, why is the voltmeter connected in parallel?
Why is the voltmeter connected in parallel? Someone online is listening. Why is the voltmeter connected in parallel here? You know, from what I said, let's look at what I said here. Let's look at it here. I said, just listen to this definition. Both your potential difference is the work done in moving a unit charge. Abi? So now, that's why I say you should listen. Some part of it can look somehow, but it's interesting. Now, your potential difference is the work done. Let me take you back to this. Except maybe that person was not in class when we were doing it in the morning. I gave you a question. I said, look at this field. This is an electric field. Abi? I said, if you are bringing a small test positive charge. I said, if you are bringing a small test positive charge, if you remember that question, I said, you are bringing a small test positive charge against a field. What will happen to the potential energy? I said something like that. This marker, if I'm taking it up, at this level, if I drop it on his head, he will feel pain. If I take it further and I drop it, he will feel pain. If I take it far further and I drop it, which one will he feel pain the more? Is it not the same marker? What is making the difference? At this level now, do I have potential energy? Yes, because it has covered the height. Abi, if I take it further, did the potential energy increase or decrease?
Increase.
And you know that it is that potential energy that will be converted to kinetic energy. So by the time I release it from that top, before it gets down, the speed and the energy it's coming with will be very, very high. And that's why sometimes ordinary rain can beat you and you'll be feeling the pain. Just water that can just splash on you like this, all because of. Just take this. Look at, let's say the earth, gravitational field always acts downward, Abi. So for the person to understand it better, let's say this is gravitational field. If I take, this is the ground, everything always comes towards the earth's surface. So if I take this marker from here to here, I've covered the height, Abi, and that will give me potential energy. But what was I doing? I was taking this from a level to a level. I'm doing work. But if I drop it, it will work on itself. I'm going against gravitational field. But if I leave it, gravitational field will work on itself. Do you get that? Same thing here. Look at the electric field. So if I take a charge, I just bring a charge. It's more like you have a magnet. I want you to get the picture clear first. You have a magnet. I'm bringing south of a magnet here. As I'm bringing the south closer, what will this guy do? Repel it. Abi. Now as I'm bringing it, the more I bring it, the more I'm feeling the force in my hand that this guy is trying to push it back. So now, if I'm bringing a positive charge closer to a positive, what will that positive do? At a point, you know, when I raise it from here to here, there's potential energy. When I raise it further, there's also potential energy. So if I say that what is the energy I will use to take it from here to here, that looks more like the potential difference. So if I now want to know the work I did from here to here, I connect a voltmeter. I'm just using the analogy. So the voltmeter will tell me what I've done from this place to this place. Same thing here. I have a charge at, let's say this is point B. Then there's a charge Q. Then I'm bringing the charge from point B to point A. So now, to take the charge, this charge definitely has a potential here. Let's call that VB, just like V here. So if I take it from point B to point A, then it will have VA. Now, at point A, will it have a higher potential or a lower potential? Just like when I take it from here, you know I'm going against the field. Here too, I'm going against the field. And the further I take it away from towards the field, the more the potential. So now from here to have a higher potential. So now if I now say, oh, I want to measure the potential energy, I'll just connect a voltmeter. Because I need to connect it to that point I'm bringing it from, to the point I'm taking it to. So at the end of the day, I can know the difference from here to here, and that is what we call your potential difference. That is your potential difference. That will be either VA minus VB or modulus or something. So now, at this level there's a higher potential, at this level there's a lower potential. So that question I asked you, if you go back to it now, when you are taking a charge from infinity or from any point to another point, you are doing work against the field. As I'm taking it up, I'm doing work against the field. So when I let go, the field will work on itself. If I let this positive now go, what do you think the field will do? To send it back. That work I'm doing here, taking it up, is the work the battery is doing here. So the battery is the one pushing it, doing that work in the field. So now, this place now, from that analogy, this place I have a potential VB. This place I have a potential VA across this guy. So now, I want to know the work I will do from here to here. Do you not expect me to just connect this voltmeter to this place? If I put the voltmeter here, what will it measure for me? It will only measure what the potential I have here. It can't measure what I've done from here to here. So you have to connect one to this place where the potential is lower to the place here, because charges go from high potential to low potential. So you connect this place and connect this place across. That's the only way you can connect them. So when you connect them that way, you're already having a junction, and when you have a junction, that is called what? Parallel connection. So that you can measure the difference between this junction and this junction. That's why we connect it in parallel. Do we understand that now? So you can look at ammeter now. Do you think I'm not trying to measure from here to here. That's why I want to know what is going on, So if you're listening, that should be understanding. So do we all get it now? So your voltmeter must always be connected in what? In parallel. And the resistance in the voltmeter, should it be low or high? Why are we making it high? To prevent the flow of currents through the voltmeter. It is still that current that will still cause the deflection. At the level we talk more about that. So it still needs current. And that's why we always say something that there is nothing like an ideal voltmeter. You people want to write post-UTM, so you should have more knowledge. It's not just draw circuits and solve questions. You have to know what is going on. And that's all of these things apply. If they are telling you in UI post-UTM now, sometimes they will ask that your potentiometer, what is the advantage of potentiometer over voltmeter? So if I ask you that, potentiometer also measures potential difference, EMF. Why am I using it? Why not use a voltmeter? Potentiometer is a better instrument than voltmeter. The reason is that your potentiometer does not draw current. That's why you are using a high resistance, but there's no way you use a high resistance, some current will still flow. so it cannot be accurate. So, but for a potentiometer does not draw current. So, which means that current, if you had used potentiometer instead of voltmeter, then you will get a perfect answer, perfect work done. That's the difference. So, if they ask me in an exam that why is potentiometer used instead of voltmeter, it's because there is no ideal voltmeter. Current always flow through voltmeter, no matter how you prevent it. But potentiometer does not draw current. That's your answer. Potentiometer does not what? Draw current. I saw most of these questions during my time, so you better know what we are doing. So let's go back to it. What is the function of ammeter, everybody? To measure current. Abi, how do you connect your ammeter in a circuit? In series. The resistance in your ammeter, should it be a high resistance or a low resistance? Think about the process. It's not about what I've said today. What I've said is just for you to understand the principles. Therefore, your voltmeter, should it be connected in parallel or in series? What does it measure? Potential difference. That's the work done. Abi? Then, so let's now go to Ohm's law. So, current electricity is simple, but there are some times that you cannot really see, and you have to get used to them. So now, what is Ohm's law? We have talked about a lot of things this morning. So we already talked about the flow of current, the potential difference, which I'll still come back to. I'll still come back to this. It's Ohm's law that gave us this. That's why I didn't say much about it. So we have what we call Ohm's law. Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference. The current flowing through a metallic conductor is directly proportional to the potential difference at constant temperature. Now, what is that? The current flowing is directly proportional to the potential difference. What supplies the potential? That's the work done. Now, let's look at what this part is saying. You can say that I is equal to 1 over RV. This is equal to VIR. That's equal to V. V is equal to IR. This is Ohm's law. So, graphically, if you are representing Ohm's law, you always have a straight line graph. Your V is directly proportional to I. If you use a graph like this, you will get a straight line. If they ask you that what is the slope of the graph, your slope is going to be just resistance. When you plot V against I, but when you plot I against V, what will be your slope? It will still be a straight line. For Ohm's law, it's usually a straight line graph. And from straight line, Y is equal to mx plus C and all of those things. The intercept will be 0 because there is no intercept here. So now, what will be the slope of this one? That's what you have to be careful. You know, if you say I is equal to V over R, that means your slope M is going to be 1 over R. It's no longer going to just be R. If you plot V, you know V is the one that is on the y-axis here. For your x-axis, it is I. Then what is M? M is usually the slope. That is your R. So R is the slope here. But if you see something like this, that means y-axis is I. Then your x-axis is what? Is V. Then your slope is going to be 1 over R. That is equal to slope M or gradients. So you have to be careful what you see. Now, most materials that obey Ohm's law, they are usually your metals. Metals obey Ohm's law, and metals are usually called ohmic conductors. Ohmic conductors. So now, come back to this place now. From Ohm's law said that V is equal to IR. So if I want to get my work done across this, All I need to know is what? The current that is flowing in this place, and that's why we needed something that will not draw the current away. So the current that is flowing here and the what? And the resistance of that resistor, then we can calculate the work done. Do you get that? So we can calculate what work has been done. If I want to know the work done across this board, if I'm using an instrument, what will I do? I will plug the V of that instrument across that board. So that can tell me the work done. That's what the voltmeter will do. But if I want to calculate it, I just need to know the resistance of this bulb. Then I can say the work done across the bulb will be equal to current flowing through the bulb multiplied by the resistance of the bulb. Sure you get? It's as simple as that. So that's what Ohm's law is talking about. Now, there are some materials we call non-ohmic conductors. Non-ohmic conductors are conductors that do not obey Ohm's law, from the word non-ohmic. So they do not obey Ohm's law because they still depend on some other factors. So they can ask you, examples of your non-ohmic conductors are majorly your semiconductors. Your semiconductors, your diode, your transistors. So these ones do not obey Ohm's law. If you draw their graph, there's a way it used to look like. The potential and current used to vary. So they are not straight due to some factors. So we will talk more about that when you get to semiconductors. So now, I'll give you questions as I used to on all of these things. But let's go on and just make sure you pay attention. I know it's not easy, but I just want us to use today to finish everything that has to do with electricity. And when you practice questions, if there's any problem, you can solve that when I come back instead of wasting time. I also have exams tomorrow, so we are all sacrificing the time. So now, what's it called? Let's now talk about resistance. So you can see that from the beginning I've been talking about resistance, I've been talking about voltage, and that's why the topic used to be a bit difficult for students. Because most of the things you need to know, you might need to talk about it first. Then before you now talk about the next before. But if you did electrostatics with us this morning, you should be able to carry on and understand what we are saying. So now, what is resistance? Resistance is simply defined as the opposition to the flow of current. Opposition to the flow of current, that is what we call resistance. The word resistance means to resist something. Just like the same way I explained capacitors, I will explain some things to you now. And most times questions come out around here. Resistance opposes the flow of currents. If I'm talking about a battery, we have two types of resistors. Not resistance now, not rheostats. We have what we call external resistance. So, for external resistance, in this place now, there is resistance of this guy, but it's connected to this battery. I hope you're following. There is a resistance of this guy. It's not everything that current will just flow through. So every material to some level has its own resistance. Electron wants to flow through this guy, but there's a bit of resistance. So this guy has his own resistance. Anything connected to the battery is called external. Anything that has to do with battery is called internal. So now, this bulb has its own resistance, so it will be addressed as external resistance. This guy has his own resistance, it will also be addressed. But if I'm talking about the resistance of a battery, then that statement is internal resistance. So your external resistance is usually represented with R. While the the second one is internal. So internal resistance is talking about the opposition of flow of current in a battery. So even battery itself has some bit of resistance. And why? If you have done electrochemistry, you will know how batteries work, how electrons move from anode to cathode and all of those things, the salt bridge, because it is chemicals in a battery that is being converted to electricity. But if you don't know much of electrolysis, don't worry. Let's just go on. So now, this is associated with batteries. This is associated with external circuits, external components. We're still going to go on with resistance. Now, let's say I want to calculate the work done in a battery. Everybody, I want to calculate the work done inside the battery, like lost voltage. Which of the resistance will I use? Is it the small R or the capital R? So the voltage drop, we usually call it voltage drop in a battery. You know our own loss gives what? IR. So that means I'll use I small r. Do you get that? If I say calculate the voltage drop in this resistor, what will I use? Will I use small r or capital R? So V drops in this guy now will be equal to I capital R. If I say calculate the voltage drop across the bulb, that means that voltage across the bulb is going to be current across the bulb multiplied by the resistor across the bulb. Are you getting the picture clear? So these are the two types. I can say total. If I say what is the total voltage drop, then I will add this and this. And that is what we call the EMF. I'm coming back to that. Current, electricity is simple, it's all go into each other. But what I've said so far is not even that difficult. You just need to understand these things little by little. So now that we know what resistance is, let's now go back to potential difference and EMF. We'll solve questions. So now, there is what we call potential difference, which you all know already. And there is what we call EMF. I would like you to get the difference there. Both of them almost mean the same thing, but they are not the same. Potential difference, what did we call it? The work done in moving a charge from one point to another point. So if I'm moving a charge across a circuit, then I talk about the potential difference. But EMF, the difference is just that the total work done in the entire circuit is called EMF. So for simplicity, work done in moving the unit charge from a point, let's say point B to another point. So that means if I say what is the potential difference, change in potential, that can be VB minus VA. Yes, Jacob. What's the question?
From India.
From India.
So he said is voltage directly proportional to resistance?
Voltage
Directly proportional to resistance.
voltage. Now, if you look at what we have here, resistance is usually constant for a particular component. Now, we can have variable resistor. You can keep changing resistance. Let's say I have analytically, let's say this is a 2 ohm resistor and this is 6 volts. Let's say I have a 4 ohm resistor without neglecting internal resistance, and this is 6 volts. Now, what will be the, please listen, what will be the current flow in this place, and what will be the current flow here? What has changed? V is equal to IR, Rabi. IR is going to be 6/2. That's going to be 3 ampere, right? But same voltage, that's going to be 6/4. And that's what? That's 3/2. That's 1.1. Now, even though it is the same voltage, you can see that the resistance is invariably affecting the current flow. Abi, can you now say, okay, this 6 volts is directly, that means that if you say something is directly proportional, that means the higher the resistance, the higher the voltage. Do you get that? But for same voltage, what is it affecting? It's only affecting the current flow. But if you are to measure the voltage in this battery, then if the resistance is higher, then you will have to do greater work. So the voltage across this resistor will be directly proportional to the resistance. The higher the resistance, the higher the voltage, because we do greater work to overcome that resistor. Do you get that?
So in the circuit is different from
it's different from the entire thing. So this is the same voltage, but now this is voltage of the battery. Abi, now let's look at this now. This is how you will know this now. Let's say 2 ohms and 4 ohms. Both of them connected to a 12 volts battery. If you connect them to 12 volts battery, from what we have here, this is 2 ohms, this is 4 ohms. Do we all agree that the same current will flow? Either it is 2 ohms or 4 ohms. Same current will flow. So now, what is the current flowing? We can quickly, we have not gotten there, but just because of that question. Let's calculate the total resistance. Total resistance is 6 ohms. Abi, total voltage is 12 volts. Abi, so total current is going to be 12 volts divided by total resistance. And that's going to be 12 by 6, and that's going to be 2. So the current flowing through 4 ohms is 2. The current flowing through 2 ohms is also 2 because they are in series. But now, what is the work done in 4 ohms? It's not the same as the total. You are going to do greater work across 4. So you can see now. So the voltage here will depend on the resistor. If the resistor is higher, then the potential you will supply will also be higher. So let's calculate the potential done here. That means the work done here is going to be equal to VIR. Abi, you know we already know the current flowing. What's the current? Multiplied by 4. 8 volts. So out of 12 volts, I'm using 8 volts here. How many volts will I use here? Just 4 volts. So if the resistance is higher, we are going to do more work. So the higher the potential. Wait. Show the person, because it depends on what the person is saying actually. So that is the thing. So let's go on. So now, I hope even from that question, you should be able to get this right. What did we do in that question that I gave? 2 ohms, 4 ohms. Now, what is that potential again? 12 volts. So I want to measure the work done across this guy. Then I'll plug the voltmeter. Parallel. Everybody, what will this voltmeter read? If you follow what we just did, what will it read? Do you see that now? You should be getting the lights now. So the voltmeter here, I'm not calculating. By the time I plug the voltmeter, from here I will read 8 volts. But do you know why I might not read 8 volts? Because there would have been an error from what we said the other time. It's not the entire current that is flowing. just a part of the current. But if I want to get exact 8 volts, which instrument should I use? Do you get it? That's the point of the story. If I want to know the work done here too, what will I do? Connect the voltmeter to this. What will this voltmeter read? 4. 4 plus 8. That's the total voltage of the battery. So all of these are what you are going to apply. But now, this is called, let me use it to explain this. This is called EMF. You dare not in your life call this one EMF. This will be called what? Potential difference across 4 ohms. Do you get that? Don't worry, it's so dry. Everything is dry. When I started, I was feeling this kind of neck pain. That's why my voice was coming out like that. So, pain will overcome pain. Now, you don't get tired. So now, from what we have here, this 8 volts is said to be the potential difference of the resistor, the potential difference of a bulb. But if I say what is the EMF of the circuit, I said that is the total work done in that circuit. And that means that is that of the battery. So you say EMF of the battery or potential difference of the components. Do you get that statement? So if I say find EMF here, EMF I mean you should find everything. And that's 12 volts. Because you might not be given this, you might just be given something else. So now, the work done in moving a unit charge from a point, that means from, let's say this is the VA now, and to another point, let's say this is VB. Do you get that? That's potential difference. What is EMF? EMF is the total work done. The total work done in moving a unit charge. Total work done in moving a unit charge from, it's not even from, down the circuit. The total work done in moving a unit charge around the circuit. That is what we call EMF. That's the total work. You know, how many volts did I pass through this? 8 volts. How many did I pass through this? 4 volts. And what is the EMF of the battery? 12 volts. That means the 12 volts is doing job. Yes, it's doing a job of 12 volts and it's distributing it. These two are called voltage dividers. So let's move on. Now, one other thing you need to know about this guy is that, look at this. If I want to measure potential difference, now these 12 volts have started working. I said something about internal, so let me do something. EMF is called the total. So if there's an internal resistance, let's say this battery has its own opposition, a resistor, then it has small r. That small r is called the internal resistance of the battery. Every material has its own resistance. Now, this internal resistance, let's say it is 1 ohm. Now look at the problem here. You can no longer get 8 and 4 here because there's a problem inside the battery itself that you have to work to overcome. Please listen. Now, what is the current flowing through this circuit? I think we calculated it the other time. The same 2 ampere will pass through the circuit round. Abi, if I say that what is the voltage inside the battery? The voltage drop, not the EMF. The voltage drop in the battery, you know, that's why I called what? IR, Abi. So now I already know my I. What's my I? 2. What's my R? It shouldn't be up to that. The voltage drop across, because if it's using 3 volts to work on itself, I mean how many? 2 volts out of 12 volts. So it's only 10 volts that will be doing the job. So now, the voltage drop in the battery now is IR. And that's going to be 2 times 1. And eventually that will give us 2 volts. So out of 12 volts, it's using 2 volts to work on itself. and that's why we call it a voltage drop. It's an error. A battery should not have internal resistance, but most times it should definitely have. Everything cannot be so perfect. So now, when you're talking about EMF, let's say this is a resistor, this is a battery, and this is your key. Let's say the key is closed from where we started from. You have your ammeter, then you have your voltmeter to measure the work done across the resistor. So from here now, this battery has an internal resistance. This is an external resistance. Then I said that what is the total work done? That's the EMF around this battery. You know, we said the total work done in moving a charge around the whole circuit is what we call the EMF. So if I say what is the EMF of this battery, the EMF is going to give me the work I'm doing externally, that's VR. You know, I'm no longer saying ER, I'm saying VR. That is the potential across the resistor. Plus the work I'm doing to overcome the resistance of the battery, and that will be V small r. So the total EMF, the total work done will be the work I did in the battery and the work I did across this guy. So at the end of the day, that's going to give me IR plus IR. But both this guy and this guy are in series, and at the end of the day, my I can come out the same current. So I can say I into R plus R, then that will give me my E. So from here I can say I is equal to E over R plus R. So I is the current flowing through the circuit, E is the total EMF of the battery, V sub R is the voltage drop in the battery or lost voltage. Lost voltage. So if I have a lost voltage, if this guy is 12 volts, then I have a lost voltage of 2 volts. That means that I can only use 10 volts to work here. I can't use the whole 12 volts. This formula has to be handy. We need it for some calculations. Now, after you have done this, what do we need? The total work done in moving a unit charge around the circuit. Listen again. If I connect this guy and I open the key, I make the key close, what will the battery start doing? The battery will start working, and current will start flowing. And by the time current starts flowing, then work will be done here. Then you have 10 volts. Let's now say I want to now measure the work this battery can do, then I plug a voltmeter. So far I closed it. This one will measure 10 volts for me. What do you think this one will measure? Like if I'm using 12 volts battery. It will only measure 2 volts as the internal work. That means the total will be 12, right? But now if I leave this key open, will current flow through this guy? That means this guy cannot do anything. So if I connect a voltmeter, what do you think this guy will read? 12 volts. So you know your EMF only when your circuit is open. I hope you're getting all of these things. So when your circuit is opened, you can determine EMF. When your circuit is closed, you can't determine EMF accurately. Are you there? So they can ask you, how do you determine EMF when you have your circuit open? So it's another thing you have to take note. So now that we know about EMF, we know about potential difference, then let's look at, we are going to solve some questions and we will analyze those questions quickly before we go. So let's look at, let's continue with resistance. So now that we know everything about potential, blah blah blah. So factors affecting resistance of resistor. So I'm not going to waste time since we already did for capacitor. Factors affecting resistance of the resistor. So what are the factors that affect resistance? Number 1, area. The cross-sectional area. Look at this. We already said something at the beginning that flow of charges brings about conduction of electricity. Abi? And what is the issue with resistance? It does not want charges to flow. I hope you are still following. If you are tired, talk so that we end it. You are the one that need it the most. JP?
She has responded.
She. Okay. What is it?
She said she understands.
She understands now.
That
Is it
what you are saying is that by connecting different resistance to same
Yes.
voltage, current changes.
because the voltage will have different work to do in different resistors. So it is the resistor that will now determine. But if they are connected in parallel, it's just like this. Our house components use 220 volts in Nigeria. In Nigeria, this fan is using 220 volts. This bulb above, everything we are using is using 220 volts. But all of them are connected in parallel. So the same 220 volts from transformer is supplying this, supplying that, supplying everything. But if I had not connected all these guys in parallel, probably when I'm connecting it, if you check the way how all these things are connected, it's in parallel. So what is doing this one? Except that the person that came to help us connect this did some kind of errors. That's why the same switch is controlling both of them. It's an error. If I switch this off, it should not affect that one. And that means that these two now, if I switch it off and if both went off, that means they are connected in series. It should not be. And now, if they are connected in parallel, it now depends on the power of this one and the resistance of this one. So if they are connected in series, if I supply 1000 volts, if this one has a very high resistance, it will use its own voltage. That one too will use its own voltage. So at the end of the day, I might be supplying the house with some 10,000 volts, and that will be very dangerous for a house. Because every resistor will use its own voltage out of it because they are in series. So the voltage will be divided. But now when they are connected in parallel, it is that same voltage that will supply them, irrespective of the resistance or whatever it is. So that's why it is dependent. And again here now, what's it called? That's connection in parallel. If I switch on, is one of the questions I asked you last. If I switch off one bulb, the other bulb should not go off. Unlike Primar's connection. So if I switch off a bulb, the other bulb should not go off. But if they are in series, if your dad is watching TV in the sitting room and all the houses or all the electrical appliances in your house, they are connected in series. And you will now go to kitchen, you on hot plate. And your dad is not, at the moment you on hot plate, TV came on. And your dad is watching TV. Maybe it's that interesting part, you now switch off hot plate. From TV, but that yellow TV. So the above TV that your dad is watching. And that moment, just know that go and park your load out of the house. So, but all the appliances are connected in parallel. So whatever you are switching on somewhere does not affect any other thing. So thank God she gets it now. So now, flow of charges. So let's go back. Please, what's it? So now, area. Now for area, let's say, look at this resistor. This resistor is built this way. Now this resistor is built this way. Same length. I connect this wire. Let's just say this is a wire. And I want the electron to flow from here to here. In this wire, there are several atoms. An electron will have to flow across the atoms. If I have a tiny wire and I have a bigger wire, which one do you think it's easier for electron to flow from here to here? Between A and B. Which one? Between A and B. Which one do you think electron find? These are my resistors now. This resistor is made with a smaller area. This resistor is made with a bigger area. So which one do you think we allow current to flow? We allow electrons to move easily. I leave this door open, very big, and all of you want to come in. And I made the door very small, and all of you want to come in. Which one allows you to pass easily? So the bigger the area, the lower the resistance. Do you get that? So that means I have a silver screw related to it. That's number one. Number two, length. Length also affects resistance, the length of the wire. You have a wire that is of the same area, and all of this area thing, think about them, because there are some questions that you just want to test your knowledge, and the way they will give you those questions, you might not even need to solve anything, but you might pick up pen and start solving to the end, and you get an answer.